Hey guys, so today I'm going to walk you through a quick example of how we can use a matrix to solve a system of linear equations, kind of like what we have seen here. So let's just jump right into it. So I have this system of three linear equations, and essentially what I want to do is I want to define or start by defining these three equations with a single matrix. So I'm going to kind of draw myself some brackets. And then if you remember from yesterday when we talked about an augmented matrix, we have both the left-hand side of the equation and the right-hand side of the equation. So I'm going to just draw that little line there to kind of denote where one ends and the other begins. So I'm going to put up at the top here a little reminder for you guys. So here's my x's, here's my y's, here's my z's, and then we'll call these like the solutions or the right-hand side of the equation. What we had done when we create an augmented matrix is we basically just take all the coefficients from each one of these equations and those become the elements of our matrix, right? So for the first equation, my x coefficient is 1. For the y value of my first equation, it's -2, or the coefficient is -2. And then the coefficient on the z for my first equation is 3, and the solution, or the right-hand side of the equation, is just 9. Okay, so I'm going to do that same thing with the second one. So I have -1, -1, 3 for my y. And then notice how there's no z value. It's because our coefficient on the z is actually just 0. And then the solution over here is -4. So then I have a 2 here for my third equation. I have -5, +5, and then 17. So this is the matrix that describes this set of linear equations, okay? So, but when it comes to actually solving this thing, what I actually need to do is I need to make some changes to this matrix. The same way that I tried to multiply and get things to cancel over here so that I can solve for one variable and start plugging that variable in, I want to do the same thing with my matrix, essentially. So what I want to do is I want to make my matrix go from looking like this guy in black here to the guy in red. And what I want to do, and I'll explain it in a second, is make my matrix look something like this. Okay. And the reason is, if you think back to when you were solving systems of linear equations in algebra, the first step was always to try to solve for one of the variables, right? So let's say that the variable that I wanted to solve for was z, right? In order to solve for z, I would do some manipulating. I would get rid of, I'd find a way to cancel my x's. I'd find a way to cancel my y's so that I'm left with just one variable, z. And then when I'm left with just one variable, z, I have z equals something, right? So now I know the value of z. Essentially, that's what this is saying. So I have a 1 here in the z placeholder because what this is telling me is that I've canceled out my x for my third equation. I've canceled out my y for my third equation. And all I'm left with is the z value equals some solution. We'll call it the solution of equation 3. Okay, so essentially I now have a value for z. Well, back in algebra, what was the purpose of getting a value for one of the variables? It was so that you could take that value and plug it back in to one of your other equations, right? So once I plug that into one of my other equations, so this equation, the second equation here, I canceled out my x variable. I left my y variable and my z variable. Now, I just figured out from the third equation what the value of my z variable is. So I'm going to plug that into the second equation so that all I'm left with is this, essentially the y variable, and I've got it equal to, again, some solution. So now I know the value of z, I know the value of y, and guess what I can do? I can take both of those things now, and I can plug them in. I can plug them in to my third equation, which will help me find the value of my final variable, which is x. Okay, and we're going to use solution 1 for that. So essentially this is what this does. This is the exact same thing that you did in algebra, where you first find one variable, then you use that variable to find another variable, then you use those two variables to find the third variable. That's all we're doing here. The difference is that when we put it in a matrix like this, you might be able to notice there's a little bit of a pattern. Notice how there's like a diagonal line of separation here, where everything above this line and to the right is all ones, and everything below that line and to the left, those are all zeros. So essentially what this tells me is that I canceled out my x variable here, I canceled out my y variable here to find my z variable. Then in the second one, I canceled out my x to find my y, and I already knew z. And then the third one, I didn't have to cancel anything out, or the top equation. I didn't have to cancel anything out because even though this equation is written with 3 variables, I knew the z from the first equation that I solved. And then I also knew the value for y from the second equation that I solved. So the ones basically represent numbers or variables that I've solved for, and the zeros represent the ones that I canceled out to solve for the other ones. Okay, so again, the whole purpose of doing this with a matrix is so that you have sort of a check built into place. So if you draw a diagonal line and you can't separate the ones and the zeros, let's say you have like a 1 down here. Okay, this little random 1 guy is floating around down here. Guess what? Now you know you did something wrong, because after you're finished with all of these steps and finding your x, your y, and your z, you shouldn't have any 1s down here below that diagonal line. Everything on this side of the diagonal should be zeros, and everything on the upper side of the diagonal should be all 1s. Okay, and we'll get into a little bit more of that when we start doing an example, but for right now, this is the pattern that you're looking for, is that you can slap a diagonal across that matrix. Everything on the upper right hand side is going to be 1, and everything on the lower left hand side is going to be 0. So I'm going to pause this for a second, and then we're going to jump into an example.